Hello, welcome to Vegetable Calculus. In this video, we are trying to find the area of this onion slice. The only difference between last problem and this problem is that in the last problem, this onion slice has its center at the origin. For this problem, the onion slice has a center here, which is the coordinate 0, 1. Sorry, 1, 0. 1 is for the x coordinate, 0 is for the y coordinate. In rectangular coordinates, the equation of a circle with center a comma b is x minus a whole square plus y minus b whole square is equal to r square, where r is the radius of the circle. So a is 1 here, so x minus 1 whole square plus y minus 0 whole square is equal to r square. Because the center is at 0, 1, the distance from here to here is 1. So radius is 1 square. X square plus 1 minus 2x plus y square is equal to 1. 1 and 1 cancel, or if you subtract 1 from both sides of the equation, they both vanish. To convert from rectangular coordinates to polar coordinates, we use these magical formulas. X is equal to cos theta and y is equal to sin theta. So x square is cos square theta minus 2 cos theta plus sin square theta is equal to 0. Cos square theta plus sin square theta is always 1. 1 minus 2 cos theta. Sorry, I forgot r cos theta, r sin theta. So r square, r square. So this is r square minus 2r cos theta is equal to 0. So r minus 2 cos theta is equal to 0. This gives r is equal to 0 and r is equal to 2 cos theta. So these are the two equations. We should probably eliminate one of them for the area of the circle, the outermost circle, in polar coordinates. Clearly r is equal to 0 is not the case, because r is equal to 0 is just a dot at this 0. So only possible case is r is equal to 2 cos theta. So r is equal to 2 cos theta is the equation of this circle. The reason why r is not independent of this theta is clearly r is not like this. R is only confined to the fourth quadrant and the first quadrant. So r is dependent on theta. Now let us set up the double integral. Because we are trying to find the area, we need double integral. So we have to freeze one of them to determine the limits of integration for the other. For this case, let us freeze theta. So at a particular theta, remember from the last chapter, particular theta is nothing but a ray like this. So at a particular theta, let me draw a ray here if I can. Oh, it's kind of hard to draw a ray, so I'll use a pen. So at a particular theta, how is r varying? R is varying from 0 till this point, and we just saw the equation is 2 cos theta. So at a particular theta, r is varying from 0 to 2 cos theta. So these are the limits of integration for r. Now what are the limits of integration for theta? How do you want your theta to vary along all these rays? So if you see clearly, this one here is negative pi over 2. So theta should vary from negative pi over 2 along all these rays and should reach the topmost, which is pi over 2. So those are the limits of integration for theta. See here for this example, the theta is not varying from 0 to 2 pi. It's only varying from negative pi over 2 to pi over 2 because there is no theta in the second and the third quadrants. So limits of integration for theta are negative pi over 2 to pi over 2, and we know the area element r dr d theta. Okay, now unlike in the previous problem, we cannot do these two integrations separately because r is dependent on theta. So we cannot do both the integrations separately. We should work from this integral, the innermost integral, to the outermost integral. So let's do r dr. We'll get r square over 2. The limits of integration are 0 to 2 cos theta. Sorry, I wrote this in a confusing way. That's pi over 2 and this is 2 cos theta. These are separate. So r square is 2 cos theta whole square. So 2 square cos square theta over 2. I'm not worried about that 0. That gives 4 over 2 cos square theta. I can also write it as 1 plus 2 cos theta over 2. If you see the trigonometric formulas, you'll find this. 1 plus 2 cos 2 theta. Oh, sorry. 1 plus cos 2 theta over 2. This is the trigonometric formula for cos square theta. 1 plus cos 2 theta over 2. So these two cancel and you have 1 plus cos 2 theta, and still you are doing the integration from negative pi over 2 to pi over 2 d theta. So this two denominator, everything is gone. All you are left with 1 plus cos 2 theta. The integration of 1 d theta is theta. Integration of cos 2 theta is sine 2 theta over 2. From negative pi over 2 to pi over 2. Okay. Sine at 2 pi, like 2 multiplied with pi over 2, 2 and 2 cancel. Sine at pi would be 0. Similarly, sine at negative pi is also 0. Sine is 0 at all negative and positive multiples of pi. So we are not worried about substituting these two in sine 2 theta. So let's only substitute them in place of theta. That gives pi over 2 minus pi over 2. That gives pi plus pi, which is 2 pi over 2. 2 and 2 cancel, so we get pi. We can also do this in other way. We know the area of circle is pi r square. We know the radius is 1. Pi multiplied with 1 multiplied with 1 is pi. You can also do that way. But if you don't know what the area of a circle is, or if you are using this for a 3-dimensional problem, it's good to work out this way, breaking up in steps and doing the double integrals. Thank you for watching. See you with another vegetable next class. Bye.